So go to this cube, right? Go to this cube, right? So if you have Gmail, try to create a sign up. If you have Gmail, try to create a login over here. So it will take 2 to 3 minutes. So once you logged in, you can see default workspace. So you can click this. Okay, so you can select free 2V CPU 4 GB RAM. So what I will do, I'll mention each and everything. So visit this web page. Try to create a Gmail, a login using your Gmail account or any account. Gmail or any mail account. Login in Break. I'm not showing slide. I'm just showing browser. So don't worry. Is my screen is visible? Browser visible? That's all. Visible, right? Okay. So once you're logged in, you can see dashboard. So in this dashboard, you select free, yes, free 2 version. Yeah, audio is there. Free 2V CPU 4 GB RAM. Select this and launch, click launch lab. So all of you please do this. I will share this Python file with you if it is possible. How to share file? I'm not able to share. So what I do, I try to copy each and every code. I'll share here. I will share this file in Canvas also for understanding. I am sharing this. So select new notebook, select new notebook, and here you can see Python 3. Okay, try to select Python 3. Select new notebook and select kernel as Python 3. So paste here that code and try to execute. So we define an XOR function. So we define an XOR function. So next what we did, we try to generate Simon function. We try to generate Simon function. If you are not able to execute, don't worry, I will share this code in Canvas. So wait for some time. So no error. We define two things. We define two things. We define XOR function. We define generate Simon function. Next, what we did, we tried to find this secret string using classical algorithm. So brute force we are doing, each time we try to do one by one combination. So execute this. We executed three functions. Okay. We executed three functions. One is XOR, one is generate Simon function, one is finding as classically. I hope the same code will work in your Jupyter notebook also, Google Colab, because this is simple Python. Nothing quantum is there. Finally, we try to execute our code to check whether this algorithm is working or not. What I will do, I try to execute. So what is the input string you are giving? N equal to 4. So 4 number of bits. So what is the secret string you are searching for? 1010. And we are passing this to, we are passing this to this function. So here we are passing N equal to 4. We are passing S equal to 1010. Okay. It will try to find the secret string. I will share in Canvas after this class. So don't worry. Okay. So it will create a table. It will create a table. It try to search each and every entry with each and every pair classically. So what do you do? Try to change your number of bits. Try to change the pattern. For an example, you can give n equal to 2 and you can give 1 0. So this is possible combination. So likewise you can give. Are able to get the idea how to execute Simon algorithm classically? Is it clear? So try to modify the inputs. So you can create 5 strings and the length should be 5. So 1, 1, 0. Try to execute. It will form the string. The idea is if n equal to 5, s equal to 10110. So the length is equal to 5. You can change your input. Suppose if n equal to 2, your string could be either 0, 0 or 0, 1 or 1, 0 or 1, 1. This is the idea. Are you able to get? So n is number of bits. S is the secret string what you are giving as input. So everything is known to us. Everything is known to us. So there is no practical use of Simon algorithm, but it will theoretically prove exponentially faster than classical. That is the basic idea. Great, great. Nice. So next what we do, we try to discuss quantum algorithm for Simon problem. Okay. Whether my screen is visible, I change to PowerPoint. Is it visible? PPT is visible for you? Okay, okay. So Simon's algorithm is a scheme for solving preceding problem using exponentially fewer query to the function. Okay, exponentially very fewer query. So in order for Simon's algorithm to work, one needs to be able to implement the unknown function f using quantum logic. So before we are using classical logic using simple XOR, but here we need to use quantum logic. So we're going to shift from classical to quantum. So what are the operator we need to use? We need to use unitary operator. So if you are using unitary operator, it is reversible. It is reversible. Then it encodes the action of function f as the transformation of quantum states. So each and every time if you do any operation, okay, it will consider like unitary operation. So this is easy for Simon algorithm to retrieve previous states. Okay. So what is the crux of this Simon algorithm? In Simon words, the quantum circuit and quantum Turing machine model are equal. So whenever you create quantum circuit, it is equivalent to quantum Turing machine. But they don't know this when they created this algorithm. So after some point of time, they are able to create quantum Turing machine setting. Okay. So this is the breakthrough in all this quantum algorithm evolution. Okay. And they demonstrated these two models shortly. So whatever they created like quantum circuit, it will turn into quantum Turing machine model. So quantum Turing machine model is superset. So if you're considering theory of computation, if you're creating Turing machine, okay, it will come under quantum Turing machine. So whatever the problem solvable by Turing machine, it is already solvable by quantum Turing machine. So this is superset, this is subset. So what are the preliminary? as usual, we need to use Hadamard gate. So we use Hadamard gate to create equal superposition for all possible inputs. Input string, we can say like this. So we are applying an array of Hadamard gate for all input strings. Okay. So what is the theorem? For all a belongs to 0, 1 to the power n bit of strings. If you are applying Hadamard for all quantum states, it will lead to -1 to the power a dot b multiplied with state b. Okay. So this is dot product. This is dot product. Okay. This is input quantum state vector. Okay. So -1 is alternative function. -1 is alternative function. So what it will do, it will change a positive phase signal, into negative phase. Also, if you are multiplying the same with -1, again it will turn negative into positive. So that is why it is called alternative function. Is it clear? When you apply Hadamard gate, what you will get? You will get the output state vector B, which is multiplied with alternative state function. And we need to do for all possible output combination, which is the sum over of B belongs to 0, 1 for all possible n bit output. And what is the probability you will get? Each and every probability is 1 over 2 power n by 2. So this is for probability amplitude for each and every output quantum state vector B. So try to understand one by one slowly. So what we are doing, we are applying Hadamard gate for each and every input state vector. So input state vector is A. So if you apply this, each and every time it will change your amplitude from positive to negative. Okay. So this is your output. State B is your output state vector. So we will get output for all possible output B state vector. And what is the probability for each and every output? 1 over 2 power n by 2. Suppose for an example, if you are applying 2 qubit, if you are applying 2 Hadamard gate, then tensor product will lead to this visualization. So instead of zeros and ones, imagine +1 and -1. So this is for 2 qubit tensor product. So is it clear? Is this slide clear? Shall we move? Okay, great. So where A dot B equal to A1 multiplied with B, okay, bitwise addition with A2 dot B2, bitwise addition until AN to BN. So we are combining all input and output combination. So we are combining all input and output combination. So what is the proof? For all A belongs to 0, 1, when you apply Hadamard for A, it will lead to state 0 plus -1 to the power A multiplied with state 1. So simultaneously you can expand in such a way. Whenever if you are implementing your output state vector B, you need to do a dot product like this. So this is the general form. This is the general form. This is for all possible output combination. Okay. So we arrived until this. For all A belongs to 0, 1 to the power n, if we apply Hadamard, then you will get each and every probability in such a way. Suppose if you are multiplying A1 with B1, you will get this product. Okay. Then A2 with B2, you will get this product. Until this, you need to do AN up to BN. So this is for single qubit. This is for multiple qubit. Is it clear? This statement for single qubit state. This is for multiple qubit. See, this is for single qubit. So if you have single qubit, consider state A. If you are applying Hadamard, okay, then this is the result. This is the output. So this is for A1, A2 until AN. If you are applying Hadamard for each and everything, then your output will be this combination. Is it clear now? So this is for single qubit state. This is for multiple qubit state. Great. So finally, we need to solve this. Okay, step by step. If you are doing, you are getting a tensor product in such a way, which is similar to this. So this is for single qubit output. This is for multi-qubit output. I hope you are able to follow. Is it clear? Okay, great. So what we got as an output 0, 1 to the power n as vector space. Okay. So if you do all this stuff in n-dimensional vector space over field Z of 2, because we are doing with bitwise addition modulo 2, the usual vector space notation like subspace and dimension will make sense, right? We'll see how it gives an illusion. When you do dot product of A dot B, it will give this series, right? So this is not an inner product. This is dot product. Okay, since A dot A equal to 0, it does not imply A equal to 0. It does not imply A equal to 0. Okay, so we need to see some properties. If you are giving 0, 1 to the power n, can be decomposed into orthogonal subspaces whose dimensions sum to n, which means each and every pair which will be orthogonal to each other. So because of this property, we are able to identify the collision pair in Simon's algorithm. So for an example, For an example, 0, 0, 0 until n number of 0 is a 0 vector in 0, 0, comma 1 to the power n. But if you are looking in vector space, this is not 0 vector. This is not 0 vector. So you cannot assume a normal mathematics to a quantum linear algebra. So this is entirely different. So in Hilbert space, it is not 0 vector. So it will point to some place. It will point to some place. So that is the logic. And look at the algorithm, what I explained. So we have input qubits, okay, A1 until AN, and we have black box function. We have black box function. And this is our output. This is our output quantum state vector. And these are our ancillary qubits, which will help to identify what type of function you are doing with. Okay, so whatever the output we are getting, we are able to encode with B1 to Bn. So this will do, okay, bitwise addition with A1 to An. So that is what we got here. So whatever the input doing XOR with A, F, okay, it will do with B. It will do with B. So we don't know how clearly this F of A is computing over here. Okay, this is not clear. So what we'll do, we'll apply Hadamard gate. So all our input states, take an example of A1 until A of n, which is initialized to stage 0. Which is initialized to stage 0. If you're implementing Hadamard, what happens? It will create equal superposition. It will create equal superposition, then it will react with your function. Then it will react with your function. You apply the same concept for B1 to Bn. So here, what we are doing, we are starting from B1 to Bn. We are preparing all qubits to stage 0. So here we don't know what is the function state, but here we know what is the function state. Then what is the output of this state circuit? It will lead to the generic outcome. Now we are able to predict what this output will generate. So based upon the output, we try to predict the function type. Is it clear? In queries, we don't know the initial quantum states. That is why we are preparing from stage 0. So these are unknown states. Unknown states. These are known states in simple term. Because stage 0, we already know. Is it clear? Shall we move further? Are you able to understand this diagram? Am I audible? Okay, great. Okay, fine. So this is your circuit. This is your circuit. This is the output we'll get after execution, right? So when you try to measure this in computational basis, it will result in the random A comma F of A for all A belongs to 0 comma 1. Whenever if you apply Hadamard gate, it becomes unknown, because randomly it will collapse. Randomly, it will collapse if you do measurement. Unknown means anything. See, we need to create a quantum circuit with known state, either 0 or 1. We cannot start with unknown state. Unknown state could be anything between 0 and 1. So these are unknown states. These two are pure states, which is known. Is it clear? When you apply Hadamard, it will go to any value when you try to measure. Is it clear? May I answer your question? Okay, thank you. Thank you. So this is the output we got. So what we got, your input A multiplied with f of A. Okay, what is the probability for each and every output? Probability amplitude 1 over root 2 power n. Okay, so let's say T contains all 0, 1 to the power n contains exactly one element of each colliding pair. That is the function. F of A is your black box function. So f of A is your black box function. We don't know how it works. It is called f of A. Is it clear? Okay, okay, fine. For an example, take t equal to 0, 0, 0, 0, 0, 1, 1, 1, 0, 1, 1. Okay, so note that 0, 1 to the power n, which contains t union of t bitwise addition with r. So whatever you are giving input r, that will be bitwise addition with the union with t. Okay, therefore the output state you can write in this form. Whatever you are giving input, okay, that input is bitwise added with your A. So your function will turn into such a way. Your function will turn into such a way. So this is our input. This is our input stream. So do one by one. Do one by one in this way. So if you are giving input 0, 0, 0, your f of A will calculate 0, 1, 1. If you are giving 0, 0, 1, it will calculate 1, 0, 1. If you are giving 0, 1, 0, it will calculate 0, 0, 0. Maybe I will try to show pointer. So if you are giving 0, 1, 1, it will give 0, 1, 0. So likewise, you are able to identify pairs between them. So take an example of green. So you got the same output. Are you able to get the idea? So look for blue. Look for blue. What you got? One zero one. So this is called collision pair. This is called collision pair. So look for violet. So 0 1 1. Sorry, 0 1 0. and look for maroon. So this is called collision path. So whatever the state we got so far is this value. We already covered in previous slide. Okay. So what we supposed to do after applying Hadamard gate? Okay, we need to do measurement. If you apply measurement in your output qubit for state B, then it will collapse to for all random value A belongs to T space. So we can measure state A plus state of A XOR with R. So when you do measurement, it will give a random value. So this is always about measurement. So in classical, each and everything you need to do separate query. But in quantum, you need to do measurement to get a random output. So everything is based upon probabilistically. So what happens if you apply Hadamard for all qubit states? What happens if you apply all qubit states? You will get this sequence. As we discussed in previous slide, for each and every qubit, you will get alternative function XOR with R now. In such a way, you are able to reduce each and every bit pair. So try to separate. So look at this carefully. Look at this carefully. What happens if you measure this? It will randomly collapse to some states. Okay. So it will randomly collapse to some states. So this is what we got. I try to summarize from the previous slide. So you will have continuity if you are looking at top. So this is the equation we got. After measurement, again we are applying Hadamard. So for an example, stage 0, if we apply Hadamard gate, what will get? Positive state. Okay. Then if you are applying with function, downside, what you are doing, you are XORing with state B. So this is state A, this is state B. Okay. So this will sometimes, it will give back, kickback to your function. So accordingly, if it is reacting, it will change positive state into negative state. From negative state, if you are applying Hadamard, what you will get? You will get state 1. So this is one case. Suppose state 0, if you are applying Hadamard, it will give positive state. So this will react with your function. So if you do XOR with your state B, suppose state B is not reacting. What you get output? You'll get positive state. From positive state, if you are applying Hadamard, you'll get state 0. So this will make difference between your output. So that is why we applied 2 Hadamard gate. Before that black box function, after that black box function. And function will do bitwise addition with all your state B. What happens if you measure the state for each output B? The amplitude of state B is given in this way. If r dot b equal to 1, if r dot b equal to 0. So it means it will reduce drastically for all combination to 0 if r dot b equal to 1. Suppose if r dot b equal to 0, it will return 1 over 2 power n minus 1 for all your outputs. So this is how drastically you can reduce your query. So it will exactly point out 2 power n minus 1 elements of 0, 1 to the power n are orthogonal to R. So whichever element is orthogonal to R, you will get only that element. You will get only that element. So how we are obtaining? We are obtaining with a random function. So if you apply Hadamard, it tends to be random. It tends to be random. So your Hadamard gate will help you to identify which colliding pair is orthogonal to R. So that is your secret string. Are you able to get the idea? So this is randomly available to b dot r equal to 0. So we need to execute this algorithm n number of times to obtain n independent samples of vectors which is orthogonal to R. Which is orthogonal to R. So this will give us a system of linear equation of mod 2 from which we can solve for all the bits of R in this way. So each and every output B state vector multiplied with your R state equal to 0. So classically you need to have omega of root of 2n classical queries for successful probability of greater than or equal to 3, 4. But if you're executing using Simon algorithm, you'll get big O notation of n quantum queries for successful probability greater than or equal to 3 by 4. So you can see huge difference. Huge query difference. So this is exponentially speed up. Exponentially speed up when compared to classical. When compared to classical. So I'll try to explain the code. I'll share this code with you. You try to do just like classical, which is very easy for you. Okay. So I hope this is very basic. We are running out of time. We are importing quantum circuit and transpile module from Qiskit library, and we are importing plot histogram module from Qiskit.visualization package. And this is about Simon Oracle. Okay, so we are creating a function definition. This is function definition in Python. Okay, so for each and every bit, it will do the reverse. If you want to reverse your bit string, it will do. Okay, then for each and every bit, each and every input you are giving, it is stored in the variable n. Okay, so what is your bit string? According to it, it will create number of qubits. Number of qubits. So okay, it will multiply with 2, it will create equal number of qubits, and it will create a quantum circuit, right? So how many qubits you created, it will create those many control node. So this is for control node. This is for control node. For each and every qubit, it will create control node. Okay. If one is existing in your B string, in your input, then it will return your quantum circuit. So it will do 1-to-1 mapping. Otherwise, it will do 2:1. Right? Suppose if your bit string is 110, so consider bit string is 110. So what is the output for this? It will return 3. So the length is 3. Okay. So n become 3. So it will create a quantum circuit 3 into 2, comma n. So what is the number? 3 into 2, it will create 6 qubit with n classical bit. It means 3 classical bit for measurement. Then what we supposed to do? We need to create Hadamard gate. So how many Hadamard gate we need to create? We need to create for n number of inputs. So we need to create n number of Hadamard for given input n. Then we need to create a barrier which will separate your quantum circuit. So barrier will look like a dash. Then we try to compose our Simon oracle to the given circuit. It will create a quantum circuit. Again, we are applying a barrier. So we created 2 barriers over here. Again, we are applying Hadamard gate for all your input. So this side we created Hadamard. This side also we created Hadamard. So these 2 are your barriers. So inside this, we created Simon oracle. So this is your black box function. So imagine in such a way. Next, what you are doing? You are doing measurement. You are doing measurement for all qubits. So this will look like this. So this is your Simon oracle. This is your Simon oracle, which is nothing but black box function. So we applied Hadamard for all input qubits. Again, we applied Hadamard for all outputs of input qubits. State. Then we are doing measurement. We try to measure each and everything using classical bit. Are you able to relate all these circuits with the given code? We just applied series of Hadamard gates. Okay, for all inputs before this oracle, after this oracle. That's all. So, okay, fine. And this is the algorithm to run your plot. I won't explain. I will share with you. You just try to find out, very easy for you. So this is the histogram. If you try to plot for each and every output, and if you want to do a dot product between your bit string with the given z, so this will calculate the output. So for an example, the B, so this is your B, this is your Z. It will do dot product between B and Z, and it will give the return. Okay. So what I do, I try to share this code. So this is classical. I need to execute. Mm, File, upload, upload, files. Simon algorithm. There is no real-time application for Simon algorithm. This is for toy problem. It will help you to find periodicity. That's all. The logic is only periodicity. I try to copy this code, but it is not copying. Okay. This Simon algorithm will help you to identify periodicity. Nothing else. And finally, this is for your plot, histogram plot. Suppose if your secret string is 1, 1, this will easily show your output. So to execute this, so go to your cube, right? Go to your cube, right? So select here kernel to Qiskit version 2.0.2. So I'll delete these cells. So classically we executed. So you need to change kernel Qiskit version 2.0.2. I'll share this instruction how to install. So click environment. You need to install Qiskit version 2.0.2. So share this stuff. Qiskit. So we cannot say any particular application. It will try to find the collision pair within the given table. That's all. So it will identify with the help of periodicity. That's all. The same idea Peter Shaw used for factoring. It is always to find periodicity between your pattern in your output data. So how we are achieving this? Through randomness, through Hadamard. So I'll share this code in your notebook. We need to install environment. Okay, click here. So click add environment. You search Qiskit version 2.0.2. Then you need to install. So don't worry, I'll share instruction how to do step by step in Canvas. Okay, we executed this Simon Oracle. So no error. Then what we do, we'll construct a circuit with B equal to 110. We try to deploy Simon Oracle. I will share the instruction, all these links. So don't worry about that part. So this is the Simon Oracle generated for 110. So I need to know your input to design black box in such a way. Then finally, you need to plot histogram. So you'll get output in such a way. So I'll share all these codes. You try on your own. You try to change your input and see how to construct quantum circuit. You will get some logic. So thank you all for listening patiently. So if you are not able to follow, don't worry. Video is there. I will share material. I will share this Python code also. So don't worry about this.
Am I audible? Hello? Jay Kumar sir, am I audible?
Yes, sir, you are audible, sir.
Thank you so much, sir, for this lecture on Simon's algorithm. You have not only shown the theory part, but also shown the implementation of it. So I hope participants got some insight about Simon's algorithm. So thank you so much.
Thank
I
you,
would
sir.
request you, either you can share the material to us on the email, or we have sent you the Canvas invite, so you can directly add in the Canvas as well. So
Definitely, sir. I will share.
so as per your convenient, you can share it to us, so we can put it on the Canvas, or you can do it by yourself also. So thank you so much, sir. Thank you once again.
Thank you all. Thank you. Thank you.
Thank you.